Well, hi everyone, and welcome to the first remote lecture for Physics 2114, Electromagnetism. This is the start of Term 2, 2020, and as you know, all lectures for this term will be given remotely. I'm your lecturer for the first half of this course, weeks 1 through 5. My name is Tim Duty. Some of you probably had me for Physics 1B, and I will be recording lectures like this one and uploading them with a link to the Moodle site. So my lectures will be pre-recorded and there'll be a link for you to get to the lecture. I will try to have these lectures up by the official lecture meeting times, which are listed in the course outline, but of course you can view the lectures whenever it's convenient for you. As you know, if you've seen from the course announcements, there are additional question and answer sessions given by other people. I will also schedule an online Zoom meeting during the Friday lecture meeting time. That's 9 to 10 a.m. And this will be for discussion and questions about the lectures as well. So sometime later this week, I'll post a Zoom ID for this meeting to the Moodle course website. I'll try to use the same Zoom ID for all these Friday lecture meetings to discuss the lecture notes. Of course, you can always post questions to the course Moodle site. So usually when I finish a lecture, I will post the notes, I'll post the link to the lecture, and I'll make an announcement. And if you have any questions about that particular lecture, you can always reply to the announcement in the thread that I start for each lecture. Okay, good. So let's just get started then. And let me just say, this first lecture is just going to be an introduction to the course, and I'll also spend some time reviewing what you learned in Physics 1B, and in particular the first half of Physics 1B, which covers electricity and magnetism. I realize a lot of you probably had me last term for Physics 1231. Maybe some of you had me, but there's quite a lot of people in this course, and I'm not quite sure everyone is coming from the same course background. So today's lecture, after the introduction, I'll just go through the material that was covered in Physics 1B, just so we're all on the same page and know that where our starting point for this course is. Now, the first thing I want to say is it's really important that you go and get a textbook and read it. And so the course textbook that we're using is Introduction to Electrodynamics, 4th edition by David Griffiths. It's here, picture of it is here on the left. The library does have some copies, but I think those are limited, and the library is also only responding to requests. You can buy this book in a number of places online. It's a good book to have. It's a good reference. I recommend it. There's another textbook that I like called Foundations of Electromagnetic Theory. This is by Wrights, Milford, and Christie. And there's 3rd and 4th editions. Here's a cover from the 4th edition. This is a textbook I used actually years ago. Well, a much earlier version of this textbook I used when I was a student. So I quite like this book. It's a little bit more condensed than our course textbook, and the notation's somewhat different, but it covers pretty much the same material. So it's important to get a textbook and read it, because there's much more material in the textbooks that we can present in the lectures. And so I really want to encourage you to get a textbook and keep that around during this course. Well, there's even more of textbooks available online, and if you go to this website here, www.feynmanlectures.caltech.edu, you'll find you'll find online versions of the Feynman lectures. It's a 3-volume set here. They're very, very good, and very good supplementary material for a lot of physics courses that you might take, starting with classical mechanics, which is mostly volume 1, And quantum mechanics, next year when you take quantum mechanics, you can look at volume 3. And volume 2 is mostly electromagnetism and matter, and that's a really good alternative to look at, and it's online and it's free. So have a look at that. Okay, so how to do well in this course? Well, as I've mentioned, the lectures focus on concepts and understanding those concepts. And really, you should think of the lectures as a supplement to reading the textbook or any of those textbooks or all of them. And ideally, you want to have a look at the textbook either before or just after going through the lectures. In addition to lectures, there are tutorials, and the tutorials focus on problem-solving skills. And these skills will build on your knowledge of the concepts presented in the lectures. Of course, the exam will focus, well, it is on problem solving. So the way to do well in this course is to make sure you get good at problem solving. This is true of any of the courses you'll take in physics. So you should think of this as training, for the exam throughout the course. Like anything you want to do, you have to practice and you have to train to get better at it. And this course is no different. So the way to do well in this course is to look at the tutorials, actually work them out for yourself. So don't just look at them and say, okay, and look at the solutions and then say, okay, I understand that. The point is, take the tutorials, look at the problem, try to work it out as much as you can yourself, see how far you can get before you even look at any solution or even try to get any help, and then try to step by step get through these on your own. And if you do that, I guarantee you'll do well on the exam. And that's because the exam will focus on solving problems like you get in the tutorials or in the assignment. The same goes for the assignment, which you will get in week 5. So the point of the assignment is to make sure you're up to speed with the material, and it also gets you used to problem solving. So doing the assignment, make sure you understand the problem and solution, work them out in detail on your own, and you'll learn very, very little. If you probably will be able to find solutions on the internet, but if you just copy these, superficially, you're not going to learn anything. Of course, it's okay to get help from the internet, but of course, you have to acknowledge the sources, and more importantly, when you turn in an assignment, you need to convince the marker, which is me for the assignment, that you really understand the solution. If it's not clear to me that you understand the solution, I'm not going to give you full credit. And that's because I really want you to get good at problem solving, because that's how you pass this course. And so the assignment, just to let you know, if you go to the course website, which is, where is it? Here. You'll see that there's a course outline, there's an assessment schedule, and you'll see the assessment schedule for this course says that the assignment, actually the assignment is due, sorry, I got it wrong, it's changed from last year. The assignment is due in week 10 of this course, and so that will be given out and be marked by PHYS. The first assessment we have will be on the 3rd of July, that's during week 5, and that will be a midterm. So that will be my responsibility. I'll be making up the midterm for that course, for this course. And as you can see here again, the midterm counts 20%. And this can also be found in the course outline here if you look on Moodle. That explains the assessments and the percentage, the weight that is. And of course, this midterm test will be done online as well. And so, as I said, if you want to do well on the midterm and on the final, then prepare yourself by working out the tutorials. And so the tutorials, of course, will be record some of the tutorials. I guess this is on the next slide. So here we go. I've just copied this from the course outline. The midterm exam is 20%. It's online. It will be given on the 3rd of July, which is week 5. Probably during the normal course meeting times, it'll be done online. So if you have experience from this term 1, you know that we'll post this to Moodle. You'll have a certain amount of time to complete it, and then you'll have to scan in your solution and upload it. The same, I think, will be followed. Same procedure, similar procedure will be done for the assignment as well, which is the due date is scheduled for 7 August, which is week 10, and you'll have a week or two. The assignment will be given out a week or two in advance of this. There's also laboratory 10%, and of course the final exam will count 50%, and will be, as I said, problem solving. So you can see the Moodle site for more course, lab, and other information. As I showed you that online, of course it's here. All of you should have access to this. I also like to ask you to read the course outline document, and in particular section 6 on academic integrity and plagiarism. That's in this document here, course outline. Please have a good read through that. It's got lots of information for you. Some of it I've duplicated on lecture 1 here, but have a look at section 6 here and so forth. Okay. Now, I also mentioned the tutorials. So for my tutorials for the part 1 or unit 1 of the course, I will post these problems and exercises to the Moodle course website. And some of these will be solved in detail and presented on videos, and these will be uploaded to the course website. In fact, I've already put the first set of tutorials. If you go to the website here and you look under this folder, you'll find here tutorial 1 already. You can download it and start to work on it. And I'll put another one up probably next week, early next week. Okay? Now, I will probably give most of the solutions to these tutorials out. Some of the simpler ones I may not, though, because I really want you to work out the problems on your own. So if I do give out the solutions, it will be after you've had time to work them out on your own. And I can't say this enough that I expect you to work out the problems and exercises on your own, and that's how you learn this material for this course. Okay, I just copied this from the course outline, so you can find it in that document as well. And this is Unit 1 or Part 1, the first half of Physics 2114. And I'm not going to go through this. I just want to point out a few things. Here are the topics. We'll cover them mostly in this order. Things might get a little out of order compared to this course syllabus here. And down at the end, you see this topic, electromagnetism and special relativity. I'm not sure if we'll have time to cover that. Given that this is all done now remotely and online, I'm not sure. So in any case, this would be, if we do cover this, it'll be just for fun, just for interest. And if we don't get to this and cover it, I'll post some supplemental notes. I won't test you on this. It's just something interesting that you might find interesting. And if we have time, we'll do it. And if we don't, I'll just put the notes there for your own benefit, so you can have a look if you're interested. Okay, well, that completes the introduction of the course, and now I'll start with what I'd like to do, as I said, is review what you had in what we call Physics 1B, which is Physics 1231 or 1241, and in particular, it's the first half of that course. And I know a lot of you had that, or some of you may have had this just recently, that is last term, T1, and I think if you had my course of 1231, you realize I think before the COVID-19 restrictions, we got to almost the very last lecture, live, that is. I think what the last lecture or the last lecture or two, of course, was done remotely. But I know due to the change to T3, there's a number of students that haven't had, that had Physics 1B probably over a year ago. And then, of course, we have a number of students coming in from other places. So the rest of this lecture then will be just a review of what was covered in Physics 1B that I expect you to be familiar with coming into this course. Okay, so let's start. Well, I'm going to skip some of the very, very introductory part of Physics 1B, and we'll jump right into the important stuff. And that all started with, of course, Coulomb's law. And I'm pretty sure you remember what Coulomb's law was. Coulomb's law gives the electrostatic force, and so it depends upon the product of two charges. So the simplest situation is we have two charges, Q1 and Q2. They have some charge. Here I've written it as positive charges, and we found that the electrostatic force depends upon the product of the two charges and their separation, r, which is the distance here. And of course, the electrostatic force is a vector, and we express that by writing Coulomb's law in this vector form, where F1 is the force on charge 1 due to charge 2, which is, of course, minus what we would call F2, the force on charge 2 due to charge 1. And we wrote it in this form, the 1 over 4 pi epsilon naught, the product of the charges, divided by the distance squared. And since it's a vector, we give it its direction by this unit vector, r12, which is a unit vector that points from 2 to 1, as I've drawn here. So we can write this all this way. Sometimes we lumped the 1 over 4 pi epsilon naught into some constant we called k. If you prefer doing that, well, we did that in 1B, but we'll mostly write it like this in this course. And of course, like I said, this r small hat 1, 2 is the unit vector, so it's the vector r12 divided by its magnitude. Right. And well, multiple forces, if you have multiple electrostatic forces acting on a particle, then the net force is the vector sum. Of course, just like you learned in Physics 1A, some of the forces, you have superposition. So that's Coulomb's law. Well, and Coulomb's law is, the very basic of what is really what's going on, but of course it's not that useful in a lot of situations, and so we showed in 1B that it's more useful to define what we call the electric field, and we do that by imagining we have some fixed charge, Q2. So in this example, we could think of Q2 as some fixed charge, and we consider our Q1 here as some test charge that we can put anywhere we like. Let's imagine we put it anywhere we like to sample the force produced by Q2, and our test charge Q1 feels the force everywhere we put it. So we could use this to map out a so-called force field that we regard as arising from Q2, and it exerts force on an arbitrary charge. So in other words, the electric field, we'll write it capital E vector sub 1, can be determined as the force per unit charge on Q1 due to Q2, and we write it this way then, such that the force is Q1 times that field, right? And if you remember how we did that. So you can consider in some ways that this electric field E sub 1 describes something around this point where R1, where the Q1 is located, even if Q1 were not there, and just call it, that's the electric field. And since, as we showed, or we discussed already, forces add as vectors, from any charge we could take this E field to be the sum of electric fields from each charge, or in other words, like forces, the electric field obeys superposition. And why is this useful? Well, in many cases we'll have distributions of charges, and we'll want to know what the force is at some point. And rather than doing all the bookkeeping involved in calculating forces, we'll be able to calculate the electric field. And in fact, we'll soon see what are known as Maxwell's equations, and they will tell us about the properties of the electric field and how to calculate it when charges are around in a very general sense. So the electric field becomes very, very fundamental for us, well, in 1B, in Physics 1B, but more importantly in the course, this course. And we, in 1B, we discussed a number of situations, and we worked out some things I'll cover here. We basically looked at electric fields produced by static charges, and then we actually considered electric field lines. Well, we had the electric field, we introduced the concept of electric field lines, and we basically discussed how electric fields behave near conductors. So we had both fixed charges, and we had conductors where charges can move around, and the important property of conductors that the charges move around so that they exclude the electric field from inside the conductor, and this had a number of implications. One was this meant that if we look at the electric field near a conductor, we find that the electric field near any conducting surface is always perpendicular to the surface when we have electrostatic equilibrium. What do we mean by that? We mean when all the charges have moved around so that they cancel the electric field inside the conductor. And we showed that, a number of ways we could show that this property, but the simplest way to understand is if, of course, if the electric field wasn't perpendicular at the surface, there would be some forces and charges would move around. So by definition, you're not in electrostatic equilibrium. So electrostatic equilibrium means charges have moved around in such a way to cancel out the electric field inside the conductor, and they're not moving anymore. And this has the effect that the electric field lines near the surface of a conductor are always perpendicular, as shown here. We went on in 1B and we did a number of calculations. We showed that if we specified a distribution of fixed charge, we could always calculate the electric field using this property of superposition, and we worked out a number of examples, if you remember. Here's one example we had an electric field for an infinite, I should say fixed line of charge. That is, we imagine these charges are in a rod and they're sort of bound in some way that they don't move around, so it's not a conductor, but it has a uniform density, we call it lambda, that is the amount of charge per unit length. And we wanted to find that if we had this infinitely long line of charge and we were at some point here, P, a distance y, away from this line of charge, we wanted to calculate the electric field. And, and remember, rather than jump straight in and start calculating, and when you have problems, you should ask yourself, well, what do I expect based on the symmetry of the problem? And obviously, the electric field should not depend on where you are going around this line. As long as you're the same distance for it, it has to be symmetric. And so, which tells you if we're looking sort of down the wire, the electric field has to radiate out this way from the wire. And before you even start calculating, well, you could actually work out a number of properties. You could also show that, well, I have contributions from small units of charge here from the line here, and I'll have another contribution here. And so the horizontal components, the horizontal component of coming from this charge will get canceled out by the one here. And so in the end, you know that the electric field can only point using the notation here in the so-called y direction here. So it does look like this. And we worked that out just without doing any really calculation, just by arguing, by physical argument. And then, of course, to actually find the electric field, we had to sum up all the contributions from these small charge elements. That means we have to do an integral. And we did that, and we found that the electric field was only in the radial direction, pointing outward, if this is positive charge as drawn here. And we found that we could do this integral, and there's a number of ways we could do it. We did it different coordinate systems. We even did it for a finite size rod, but of course it's much easier when this infinite rod or line of charge is infinite. In that case, we found that the electric field, the magnitude of the electric field, was the charge density lambda divided by 2 pi epsilon naught y, where y is this distance from the line of charge. So it falls like 1 over y instead of 1 over r squared, which is how the electric field of a point charge, of course. Anyway, go back, and if you still have your notes, look at that and work that out. It's good to work that out in detail and know how that comes about. Of course, we did this by direct integral calculation. We also showed, and we'll get to this later in this lecture, that we could do this using Gauss's law. Another problem we did, and I won't go through this, is we found the electric field by direct calculation, direct integration for an infinite sheet of charge. And we imagined this sheet of charge had a uniform surface density sigma, and we're at some point P, which is a distance y away, and we found a calculation that sort of paralleled the one for the infinite line, but of course we use different elements of charge, and like I said, go back and look at your notes for this. But for an infinite sheet of charge, we find that the electric field is constant, and it has a magnitude sigma over 2 epsilon naught. So that's the kind of calculations we did for the electric field in Physics 1b. Now, we went on and we said, well, if we know what the electric field is from one charge plate, and we can use superposition, and we could work out problems, for example, like finding the electric field between two large charged plates. And we imagined that, for example, if one plate is positively charged or has some positive charge density sigma, and the other has some negative charge density, the same density but negative charge sigma, of course in the middle with the electric field from both plates is in the same direction, and if this distance between the plates is very, very small compared to the length, we could ignore these edge effects, and so we could just use the result from two infinitely large charged sheets, and we can find, of course, the electric field between the plates, and it's just sigma over epsilon naught. And of course the sigma, if we have some finite size system that's very, very large, has large area, but this distance is small, we can use this result in the middle, and this charge density is just the total charge divided by the area. And we also worked out, remember we discussed the experiment, the Millikan, and that a point charge and a gravitational field would hover in this field if the force due to gravity was equal to the force coming from the electric field in this relation, and of course that's the basis of one of Millikan's experiments on charge quantization, that if you remember from last year. Okay, we also discussed electric dipoles, and we defined, we actually said, well, we'll have a really simple model of a charged dipole, and for the simple model, a dipole is just a rigid arrangement of two opposite charges, like drawn here. We imagine we have a charge minus q and a charge plus q, and they're connected by some rigid rod that keeps them precisely at this distance d. We showed that this dipole has a vector dipole moment that we wrote as small p, it's a vector, of course, and the direction is given by the line from the negative charge to the plus charge. So here's my dipole moment p in this diagram for this example. And we showed that the dipole moment had the magnitude of the dipole moment was q times the distance. So it had units charge times distance. And for this very simple example, it's just the magnitude of the charge of each charge, which is equal in this example, times the distance. And with this definition, why do we define this dipole moment? Well, it's easy to see for this definition for dipole moment P, then in a uniform electric field, for example, as drawn in this diagram here, that we could actually work out the torque. You remember what torque is from Physics 1A, and using this definition, it's very easy to show that the torque can be written very simply as this dipole moment P crossed with the electric field E. Well, we also discussed that if the charges are equal and the field is uniform, it's easy to see that the net force on the dipole is 0. Of course, if the field is not uniform, there will be a net force on the dipole, and you can work that out. Okay, that was our introduction to dipoles. So once again, the torque, I'll just skip through this. But if we work out the torque, we could see that the dipoles tend to align with this dipole moment parallel to E. And this course will eventually, when we come to polarizable materials, will show that having a lot of dipoles is the basis of a dielectric, and we'll learn how to work that out and describe that in a bit more sophisticated way than we did in Physics 1B. Well, we could also, instead of working with forces, like in other problems, we can work with we can consider the work done to rotate a dipole, and we can consider the potential energy, which we could write in this form as minus P dot E, of course, which is minimum when P is parallel to the electric field. Okay, well, that was Coulomb's law and the electric field and dipoles. And after we completed that unit in Physics 1B, we moved on to another interesting way to treat electrostatics, which is known as Gauss's law. And the idea of Gauss's law is pretty simple. Well, at least the idea is. And the idea is that we imagine we can determine, we have some charge distribution, and we have some imaginary box or closed surface, and we saw that we could actually figure out what the charge is inside this surface by looking at the fields going in and coming out of the surface. So a little example we had was, imagine we have this sort of, well, this is in 2D, but we can sort of imagine this in 3D, and we draw this surface around this charge of plus 2q here, and if we looked at the number of field lines coming out of this, and we compared it to a situation where we had a box drawn around our single charge, or charge of minus q, we see that, well, here we have 8 field lines going in, and here we have 16 going out. And so the idea is that if we could properly count somehow the field lines in going through our imaginary surface, where the sign, of course, counts, that or sound, of course, is important, we could somehow infer the charge inside the box. Well, that's kind of what, in a hand-waving way, Gauss's law tells us. And to make this quantitative, instead of just this little cartoon here, we had to introduce the concept of electric flux. And so what we showed in Physics 1B was that Gauss's law relates the electric flux that we wrote down as this capital Greek phi through a closed so-called Gaussian surface. That's just a closed surface, and that Gauss's law related this electric flux, which is a quantity that depends on the electric field and the surface. The Gauss's law related this flux to the enclosed charge, and so the in Gauss's law simply stated is that epsilon naught times this electric flux equals the enclosed charge. And this electric flux, if you remember, is the closed integral, that is the integral over a closed surface, which is the Gaussian surface, of the dot product of the electric field times these small area unit dA. And remember, this area unit was a vector that is normal to the surface element, right? And so, for example, this small surface element dA vector, at any point it's perpendicular to the surface. And so this takes the component of E in that direction. So if E is parallel to the surface, there's no contribution to the flux. And there's a maximum contribution, of course, when it's perpendicular to the surface. So the contribution from, this is a sum of lots of contributions, and contributions that are where E is perpendicular to the surface have the largest value due to this dot product. And also the sign gets included as well, because if E is anti-parallel to this dA, then it will be a negative, right? And so that's how, and so, I mean, this is loosely speaking, this is how we get field lines going in versus field lines going out, and how we quantitatively measure, and that's what really a flux is. And so, and if we, in general, it could be very, very complicated. We could have a very, in general, we could have a very complicated Gaussian surface, and we could break this up into lots of small elements, and we could evaluate this integral E dot dA, and here's some examples of the contribution. And we'd sum up all the pieces, and we get the net flux and then closed charge. Well, in general, we don't usually solving problems, we use Gauss's law for very symmetrical situations where, due to the symmetry of the problem, we can quite easily work out the flux. That's when Gauss's law is useful to us, actually, if you remember. So, for example, here again we treat the infinite charged insulating rod. This is very similar to the infinitely long line of charge that we calculated directly, but we showed that for a situation like this, it's very easy to find a surface that allows us to find the electric field using Gauss's law. And in this case, the surface would be a cylinder, and of course we have to use we'll use our sort of physical arguments to as we did before, to say, well, if I have this rod of charge, the resultant electric field, if this is positively charged, it has to be only radial, for the same reason, for the same arguments we used previously, is that different parts, so for example, if I'm at this point here, then this the small unit of charge at this location will produce electric field, and the horizontal component coming from that, or in this case the vertical component, will be canceled by another small charge element here and so forth. So we use the same kind of arguments we do, and we know what we know some general properties of the electric field, and then we pick an appropriate Gaussian surface, and that allows us, in this case, knowing the properties of this electric field. Well, we know that this top surface, the electric field, is going to be parallel to the surface, so it will not contribute to the flux. The same for this bottom surface, and the contribution at some distance, small r here, will be identical as at any point on this cylinder, and that makes it easy for us to work out the electric flux here. And then so we can turn that around, and instead of saying, well, we find the flux, and by knowing the flux we find the charge enclosed, which would be the integral of all the charge on this rod, we can turn it around. We can use Gauss's law to say, well, if we know what the charge is, because we know the charge density, here we use Gauss's law to work out what the magnitude of the electric field is. And of course, no surprise, we get the same answer as a direct calculation, albeit in a rather, more convenient and easy way. The advantage of Gauss's law, as if you remember from Physics 1b, is that We could also use this to find the field for a finite radius rod, and we can also find the field inside the rod by modifying the enclosed by actually calculating the enclosed charge, which is not all the charge on the full rod. So remember, if you go back and look at your notes for 1B, you'll see how we did that. And in fact, we found that Gauss's law was actually quite useful in these very symmetric situations, and gave us even some results that could be a little bit difficult to get from a direct integration. Okay. Well, we used Gauss's law for a number of very symmetric situations. Here's Gauss's law for the infinite charge sheet. I'm going to skip through this, but go through this again and look back through your old notes and understand how this worked. But it's a very nice way of showing finding the electric field from an infinite charge sheet using Gauss's law. Simply because it's very easy by picking the right Gaussian surface, and there's some arbitrariness in picking the Gaussian surface, but it's very easy to find that it's only the area that's important, and you get two contributions from each side, and this allows you to find the result you found from direct calculation. So there are a number of examples for Gauss's law, and I encourage you to go and review those and have a look at that, because in this course we'll be writing equations for the electric field, and of course these are known as Maxwell's equations, and we'll get to those very soon. And you'll see that these are very much expressions of, well, at least one of the Maxwell's equations is very much an expression of Gauss's law. It's just that Gauss's law is a kind of integral form of one of Maxwell's equations, whereas Maxwell's equation is a differential form. But it's really the same content. So the point of going through a review of 1B and remembering what Gauss's law and later on Faraday's law and all these things you learned in 1B is to have these, to realize that in this course we're going to be looking at pretty much the same physics, but we'll be doing this in a much more sophisticated way, and it's very useful to know how the simple way of looking at things, of course, to have a really good feel for that before you jump into the more complex and sort of vector calculus way of thinking about electrodynamics. Okay, so I'll continue with this review of Physics 1B, but I just had a look at the time, and already we're sort of above 40 minutes. I guess this is taking a bit more time to do a remote lecture than I expected. So what I'll do is I'll finish the review of electrostatics and conclude lecture 1, and I'll continue with the magnetostatics from 1B as a review in lecture 2, just so I don't have files and lectures that are too long. Okay, so we discussed so far now Coulomb's law, Gauss's law, and mostly we were thinking about fixed charges, although we did mention something about conductors. But it's important to realize that, as I mentioned earlier, that there's a bit of difference between situations with fixed charges, which are in principle easy. You have some fixed charge, you work out the electric field using a number of methods, and that's pretty much a pretty simple set of problems for situations such as that. Now, it's a bit more complicated when you have conductors present, if you remember from Physics 1B, and that's because, well, conductors by definition are materials where charges can move around essentially freely, and so when you have conductors present and you place them, for example, in regions where there are fields, charges will move around until one has electrostatic equilibrium. And so that makes problems with conductors are typically a bit more difficult to get a grip on and to solve. So let's just discuss conductors and electrostatic equilibrium again. So as I said, we have a conductor or set of conductors, and we put them in electric fields, charges, there are forces on charges, and they will move around until there's no field left in the conductor. And that is because if there were a field left, the charges would continue to move around until they screen out the electric field. So electrostatic equilibrium is established when there's no net motion of charge within a conductor, and the conductor is said to be in electrostatic equilibrium. So electric field is everywhere inside the conductor, and that means if an isolated conductor does carry a charge, the charge resides on the surface. And we discussed this at length in Physics 1B if you want to go back and look at your notes for that. And as I said, we showed in a number of ways that the electric field just outside a charged conductor is perpendicular to the surface, and it will have magnitude sigma over epsilon naught, where this sigma, this charge density per unit area, it's a two-dimensional charge density, that is charge per unit area, sigma. So just outside a charged conductor, the magnitude of the electric field will be sigma over epsilon naught, where this is the local charge density. So in general, this doesn't have to be a constant all over the conductor. It can depend on where you are near the surface of a conductor, but the electric field will always have this magnitude where this sigma is the local charge density. Of course, we discussed in Physics 1B, if you remember, that if you have an irregularly shaped conductor, the surface charge density is greatest at locations where the radius of curvature is the smallest. Go back and look at the notes. So, this is why electric fields are greater at sharp points, for example. Now, we discussed electric fields at the surface of a conductor, and that was most easily done using Gauss's law. And for example, we worked out Gauss's law where we're near the surface of a conductor, and so to use Gauss's law, we had near a conductor we had a surface, and here we used a cylindrical surface. It doesn't really matter if you make this small enough. If you're near the surface of a conductor, what's really important is just the area, and of course there's no electric field inside. So this you can actually work out this property that the electric field is sigma over epsilon naught near the surface of a conductor. So have a look at the details here to review Gauss's law for that. Well, after Gauss's law, during the course during Physics 1B, we did a lot with the electric field, but we realized that it was much easier to work with this concept of electric potential. And so we introduced the concept of electric potential. We showed how it was related to potential energy. And for a good part of the course, we worked with electric potential instead of electric field. And that's because electric potential is a scalar quantity. Unlike the electric field, which has three components, the electric potential is just a scalar, and practically that means it's just less bookkeeping to do if you want to calculate the electric potential. And so this makes things a bit easier. So it's much easier to calculate electric potential in general than electric field, and it contains the same information essentially, because since once you have the electric potential, of course you can find the electric field. We'll discuss that in the next slide. So we showed, for example, that the electric potential is just the potential energy divided by some test charge Q0, and you can think of that as the work done by the field in returning a positive charge Q0 from R to infinity. That is, it's the energy stored in the system by assembling it. So So we imagine we had to bring this charge in from infinity to some point, and that took some energy, some potential energy. That energy is now potential energy. And so we could write the electric potential as just this work of the work done by the field in taking its charge, for example, here from r back out to infinity, and work defined in the usual way as force times the integral of f dot ds, and electric potential we just divide by this test charge q0. And so for a point charge at r equals 0, the electric potential is very simply q over 4 pi epsilon naught r. Of course, sign matters, and there's a number of notes here. And so, well, there's some important points about the electric potential, and one of the main ones is what often matters most is not really the absolute potential, but it's the potential difference, delta V, which is basically the integral of the work done to go, for example, from A to B, and of course it can be expressed as an integral. Since electric field is force divided by charge, we can express it as this integral as well. And we discussed also that since the electric force is conservative, that this potential difference doesn't depend, of course, on the path. We showed, of course, that some properties of the electric potential. We discussed equipotential surfaces and showed they're always locally perpendicular to the electric field, and the field points from high potential to low potential, which is the direction of force on a free particle. And a number of properties, if you want to envision equipotentials, the more intense the field, the more equipotential surfaces you cross in the direction of the field. Once again, I'll skip through this quite quickly. We showed the electric potential of a point charge, and we showed that the electric field in this particular example is given by the negative derivative of the potential with respect to radius r. And in fact, that's a general property. Well, I'll just skip through this really quickly. There's, again, you can look at the electric potential of a dipole. We can work that out in detail. But the important thing, especially relevant to this course, is that you can always find that once you have this electrostatic potential, you can always find the fields as partial derivatives. So suppose I have worked out the electrostatic potential in, for example, Cartesian coordinates, x, y, z, then I can always find the components of the field by these partial derivatives. And we'll see this is just the operation of the so-called gradient in the context of this course. We used the electric potential and properties of the electric potential to derive some results for charged conductors. I'll just go through this really quickly. Once again, the electric field is always perpendicular to the surface of a conductor, and because of this, this means the potential difference at any point A and B on the surface is 0, so V is constant everywhere on the surface of a conductor. And you could also show that since all the charge resides on the surface and there's no field inside the conductor, then the potential of at the conductor everywhere on the surface and inside the conductor is the same. Here. And then finally, we having an understanding of electrostatic potential, we introduced the concept of capacitance. And showed that in many cases it's much easier to work with capacitance when we have systems of conductors. And so, well, first of all, we ask ourselves, what is capacitance and what is a capacitor? Well, we start with an example where we imagine we have two conductors, and if they're initially charged, we imagine we move charge from one to the other. So we move positive charge here, or equivalently we can think of moving electrons, negative charge, from this conductor on the left to the one on the right. And as we move, these conductors become charged up, we create electric field. And what you find, you can calculate this, and you always find that the potential difference, and sometimes we just have to realize, instead of having delta V written everywhere, well, we actually write V with a particular reference, so we can just write it as V, essentially. And you always find that this potential difference is proportional to the charge transferred. And so V is always proportional to Q, or in other words, V equals Q divided by this constant C, this constant of proportionality. And, well, why is it defined this way? Well, we usually think of Q as proportional to V. That is, the amount of charge that we've transferred is proportional to the potential difference. And that sort of amount of charge per unit volt is the capacity of the system, right? In other words, Q equals CV. And so the capacitance is this constant proportionality, and what we found in 1b is it really just depends, it's a property of the geometry of our system, the geometry of the conductors. And so we worked out a number of situations. So we found the capacitance for parallel plates, which is the sort of typical example. We found the capacitance for spherical shells of conductors and cylindricals, there's a number of a number of situations we could work out easily. So how do you calculate the capacitance? Well, at this point you really have everything you need to know to calculate the capacitance. You just calculate the potential difference. You see it's proportional to the charge, and you just read off the capacitance, let's say. So in practice that means, well, we assume we get to electrostatic equilibrium. Our conductors have some charge, plus or minus Q. We can find the electric field. Sometimes directly we can find the potential difference, but whenever we have the electric field, we can always find the potential difference by doing some integral, and we'll find that V is always proportional to Q, and you just read off the capacitance. So in principle, it's really, really simple. It's just a very useful concept, this capacitance, especially when we get to electrical circuits. And so here's some examples. I'm not going to go through these in detail. You really should know this. If you've come out of Physics 1b, I really hope you could calculate the capacitance of a parallel plate capacitor. So I'm not going to go through it. Please have a review of it. Make sure you understand it. Make sure you understand how to calculate the capacitance for cylindrical and spherical capacitors. If you go back to your 1b notes, you'll find all this done in detail. Go through that just to remind yourself how it works. Okay. There's also, if you go back to your 1b notes, you'll find an example where we start with parallel plate capacitor and we put in another conductor and calculate the capacitance in detail. And we do this in detail, and in the end we find we just added capacitors in series. And so you can see how this works. And then so 1b we learned that we added capacitors in series and parallel, and in contrast to, for example, adding resistances, in series capacitance, the 1 over the equivalent capacitance of some capacitors in series is sum over 1 over the individual capacitances, and for parallel capacitances we just add the capacitance. Of course, this is opposite to what you find for adding resistances, or for that matter of fact inductors, but you should remember this as well. And then finally we talked about the energy stored in the capacitor, and we did a number of examples. This was quite easy to show, and you can go through this in detail on your own. But the main thing is that, and we'll show in this course, we'll see more in detail that whenever we have an electric field, we can think of an energy density that's 1/2 epsilon naught, the magnitude of the electric field squared. Okay, Well, I think I'm going to cut off the review now because I've gone quite long enough. I'll pick back up in the next lecture. We'll mention just a brief thing about dielectrics, and then we'll move into magnetostatics. Still a review of 1B, but like I said, I want to make sure everyone's on the same page. So if you want to have a break and go through this part of the review, and then when you're ready, you can move on to the second part of the review. And then once we get the review of 1B out of the way, we'll do also a bit of review of vector calculus. I realize most of you have recently taken a math class in vector calculus, but also I just want to go over that to make sure we're all on the same page and using the same kind of notation. Okay, see you next time.